Right now, the moon is pulling away from you, about 1.5 inches this year, the width of your thumb. It sounds too small to matter. It is not. That same quiet drift once meant a single day on Earth lasted only a handful of hours, and it means that 600 million years from now, the sky will lose something no living person has ever had to imagine losing: the total solar eclipse. Gone for good. Scientists have tracked this retreat for decades, using laser light bounced off mirrors astronauts left on the lunar surface, and the numbers do not lie. Tonight, we follow that drift back to where it began, and forward to an ending stranger and more honest than the one most people have heard. If tonight's journey through the space between Earth and the moon made you curious, a like and a subscribe would mean the world to this small channel. We truly appreciate every one of you. So settle in, get comfortable, and let go. In 3, 2, 1, liftoff. There is a kind of comfort in the moon that nothing else in the sky offers. The stars are pinpricks, distant and cold, more idea than object to most people who glance up at them. The planets are wanderers, if you know where to look, but most people never do. The moon is different. It hangs there, full and close enough to touch with your imagination, the same face turned toward Earth, night after night. The way it has for as long as anyone alive today has been alive to look up and find it. Grandparents pointed it out to grandchildren. Sailors steered by it. Farmers planted by it. It rose over harvests, and it rose over rocket launches, and it has never once given the impression that it might do anything other than what it has always done: hang there, patient and unhurried, the one fixed point in an otherwise restless sky. That impression is wrong. Not exaggerated, not oversimplified, wrong in the plain and measurable sense scientists use the word. The moon is moving away from Earth at this very moment, and has been moving away for the entire 4.5 billion years it has existed, and will keep moving away for as long as Earth and the moon continue to share this stretch of space together. It is not a fast retreat. In any single night, in any single year, it is close to imperceptible. But it is real, it is constant, and it happens to be one of the most precisely measured phenomena anywhere in the solar system. Tonight, we are going to sit with that retreat honestly and slowly, the way a story like this deserves to be told. Long before anyone could measure the distance to the moon with any real precision, before rockets, before satellites, before anyone had left the surface of the Earth at all, one man worked out that the moon must be drifting away using nothing but mathematics, patience, and an unusually thorough understanding of tides. His name was George Darwin, an English mathematician and astronomer who lived from 1845 to 1912, and if the surname sounds familiar, that is because it should. He was the second son of Charles Darwin, the naturalist whose work on evolution had already reshaped how humanity understood its own origins, and whose ideas had made his household one of the most argued about addresses in England. Growing up there meant growing up watching a very public, very controversial argument about the nature of the world play out at the family dinner table, and it seems to have left its mark on the son as much as it did on the father's name. George chose a quieter field to work in, mathematics and astronomy rather than natural history, perhaps hoping to avoid the kind of public storm his father had weathered. Instead, he ended up building his own career on a claim nearly as unsettling in its own quiet way: the idea that the moon overhead, which every culture in human history had simply assumed was fixed and permanent, was actually spiraling slowly outward, and had been since the moment it formed. He came to that claim by way of tides, Of all things, the ordinary rise and fall of water along a coastline that most people notice only when planning a trip to the beach. George studied under the physicist William Thomson, later known as Lord Kelvin, and built on the earlier tidal work of the French mathematician Pierre-Simon Laplace. In 1883, that training earned him an appointment as the Plumian Professor of Astronomy at Cambridge University, a position built for exactly the kind of painstaking, decades-long inquiry he was already pursuing. Long before the professorship, though, the actual labor of the work was almost tediously human. Darwin spent years poring over tidal records gathered from 14 different ports scattered across England, France, and India. Some 33 years of measurements in total, painstakingly worked by hand into the mathematics of friction and momentum at a desk, by lamplight, with no calculating machine faster than his own patience. Beginning in 1879, that patience produced a long series of papers on what Darwin called tidal friction, the strain that builds inside a planet as it is stretched and released by the gravitational pull of a nearby moon. He noticed something simple but far-reaching. The tides that the moon raises in Earth's oceans do not sit in perfect alignment with the moon overhead, because Earth spins faster than the moon orbits. That small misalignment acts like a brake on Earth's rotation, and at the very same time, like a gentle accelerator, pushing the moon a little farther outward. Energy does not simply disappear in that exchange. It moves from Earth's spin into the moon's orbit, and the books only balance if the moon is, very gradually, spiraling away. From that mathematics alone, decades before anyone had a way to check it directly, Darwin concluded that the moon must have been much closer to Earth in the deep past, and that it was still receding in his own lifetime, just far too slowly for anyone to notice. He carried the idea further than the tides alone could take him. He proposed that the moon had originally been part of the Earth itself, flung free early in the planet's history, while it was still molten and spinning fast enough to tear a piece of itself loose, a scar left behind in what is now the floor of the Pacific Ocean. That particular idea did not hold up. Scientists arrived at a very different explanation in the 1970s. Largely by studying the moon rocks the Apollo astronauts had carried home in metal boxes. Those rocks turned out to share an oddly close chemical fingerprint with rock from Earth's own mantle, right down to the ratios of oxygen isotopes locked inside them, a resemblance that made far more sense if the moon had been forged from a mingling of Earth and impactor material than if it had simply broken away whole. Modern evidence now points to a violent collision, a planet roughly the size of Mars, striking the young Earth and scattering debris that eventually gathered itself into the moon we see tonight. Darwin, working nearly a century earlier with nothing but tidal tables and a slide rule, could not have known any of that. He got the ending of his own story wrong. But the middle of it, the long, slow, outward spiral driven by tidal friction, was never in question once scientists finally had a way to check. That is not to say no one tried. In the meantime, astronomers spent the decades after Darwin timing the moon as it passed in front of distant stars, an event called an occultation, watching a star wink out of view in an instant as the moon's edge slid across it, then reappear just as suddenly on the other side. Others bounced early radar signals off the lunar surface starting in the late 1950s, the same basic technology that had proven itself tracking aircraft only a decade or two earlier, each method squeezing out a little more precision than the last. But none of those techniques could pin down the Earth-Moon distance to better than a few miles, nowhere near precise enough to catch a drift of an inch and a half a year. Proving Darwin right would take something far more exact than anything available from the ground alone. It would take leaving an instrument on the moon itself. To understand how anyone finally managed that, it helps to go back to a single, sweltering week in the American summer of 1969. For years, by that point, the United States and the Soviet Union had been racing toward the moon, a contest that had grown out of a promise an American president made to Congress in 1961, that the nation would land a man on the moon and bring him home safely before the decade was out. That promise came less than 4 years after the Soviet Union had stunned the world by launching Sputnik, a beeping metal sphere no larger than a beach ball, into orbit in 1957, an achievement that left many Americans genuinely afraid their country was falling behind in a contest that suddenly felt like it might decide far more than bragging rights. Rockets had failed on their pads. 3 astronauts had died in a fire during a launch rehearsal 2 years earlier. And still, on the morning of July 16th, a Saturn V rocket, taller than a 30-story building and burning through more than 4.5 million pounds of fuel in the first minutes after liftoff, carried 3 astronauts away from Cape Kennedy in Florida: Neil Armstrong, Buzz Aldrin, and Michael Collins. 4 days later, with Collins circling alone in lunar orbit aboard the command module, Armstrong and Aldrin guided a spindly, 4-legged lander named Eagle down toward the surface, past a computer that kept sounding alarms it had never been tested for, past a landing site littered with boulders that forced Armstrong to fly the final stretch by hand, with something like 25 seconds of fuel left in the tank. They set down on a plain called the Sea of Tranquility, and some 6.5 hours later, Armstrong climbed down the ladder and became the first human being to stand on another world. An estimated 600 million people around the globe, roughly 1 out of every 6 human beings alive at the time, watched or listened as it happened, which remains one of the largest shared audiences for any single event in human history. Families across the country gathered around television sets that summer night, watching grainy black and white footage beamed across that same vast distance, the picture flickering and softening the details, but unmistakable all the same. A human boot pressing down into grey dust that had never once been disturbed by anything alive. Given everything riding on those next 2.5 hours on the surface, a person might expect the astronaut's checklist to have been filled entirely with flags and photographs and speeches. It was not. Alongside the American flag, the sample bags, and an instrument built to measure moonquakes, Armstrong and Aldrin also unpacked something almost comically modest by comparison: a small panel, not much larger than a suitcase, that Aldrin set down in the dust and carefully leveled using a built-in bubble gauge, angling it to face Earth as precisely as he could by eye. It was called a retroreflector, and unlike nearly everything else on that checklist, its job had nothing to do with anything happening on the moon that day at all. It was built to sit quietly on the surface for decades, doing nothing but waiting for a beam of light to find it. It did not have to wait long. Within days, observatories back on Earth began firing laser beams at that small panel, aiming across roughly 238,000 miles of open space at a target smaller than a card table, and listening for the faint return. 4 more retroreflectors followed in the years afterward, 2 left by later Apollo crews, and 2 carried by Soviet robotic rovers named Lunokhod 1 and Lunokhod 2, each one roughly the size and shape of a bathtub, set on wheels, solar-powered, driven by a team of operators sitting in a control room outside Moscow, steering by watching a delayed video feed beamed back across that same 250,000 miles of space, part of a parallel and entirely separate program, racing toward the same conclusions from the other side of an ocean and an ideology. Together, the 5 mirrors turned the moon into one of the most precisely measured objects anywhere in the solar system. There is something almost tender about that arrangement when you sit with it. Of everything humanity has ever placed on another world, one of the most enduring scientific contributions has turned out to be a handful of small, silent mirrors doing nothing but reflecting faithfully for 56 years and counting, long after the astronauts who carried them there have grown old or passed away, and long after the rivalry that first sent them there quietly faded into history. The trick behind a retroreflector is simpler than it sounds and rather elegant, and you have almost certainly seen the same principle at work without ever noticing it. It is the reason a bicycle reflector or a strip of highway road sign throws your headlights straight back at your own eyes at night, no matter what angle you approach from. An ordinary mirror only bounces light back the way it came. If you angle it exactly right, the way you have to tilt a bathroom mirror just so to catch your own eye in it. A retroreflector is built differently. Each tiny mirrored corner is cut so that light entering from almost any direction bounces off 3 internal surfaces in sequence and exits, heading back precisely the way it arrived. No matter how the panel happens to be tilted toward Earth on a given night, it does not need to be aimed, it only needs to be found. Finding it is the difficult part. Observatories such as Apache Point in New Mexico, set high in a stretch of quiet desert chosen for its dark skies and steady air, and the Côte d'Azur Observatory on a hillside in France, fire short pulses of laser light through large telescopes, aiming at a mirror roughly the size of a dinner tray, sitting on a world with no atmosphere to steady the view, 250,000 miles away. Earth's own atmosphere blurs and scatters the beam on its way out, spreading a tight point of light into a faint patch of illumination, miles across, by the time it reaches the lunar surface, so that only a tiny fraction of the photons sent out ever have any chance of striking the reflector at all. The telescope has to track the moon's motion across the sky continuously while firing, correcting for the fact that the beam takes a little over a second to arrive, and the reflected light takes just as long to return, aiming, in effect, not at where the mirror is, but at where it will be by the time the light gets there. Of all the light that leaves the telescope, only a vanishingly small fraction ever makes the full round trip back, sometimes as little as a single returning photon for every few quadrillion sent out into the dark. On many nights, the atmosphere is too turbulent, or clouds roll in, or the returning signal is simply too faint to separate from the ordinary noise of starlight and instrument static, and the astronomer goes home with nothing to show for the evening but another small subtraction from a very long list of attempts. But a single photon arriving at the right instant is enough. By timing that round trip to within a few dozen picoseconds, a sliver of time so brief that light itself only travels about an inch during it, scientists can calculate the Earth-Moon distance to an accuracy of roughly 1 millimeter, a precision finer than the width of a pencil lead, measured across a gap wide enough to line up 30 Earths side by side. That precision is not spent only on measuring the recession. The very same laser pulses that reveal the moon inching away have also let scientists probe what lies beneath the lunar surface, tracking faint wobbles in the moon's rotation that hint at a molten layer deep inside its core. The way a raw egg wobbles differently than a hard-boiled one when you spin it on a countertop Scientists have used the timing of those returning photons to test Einstein's theory of general relativity itself, checking with extraordinary precision whether gravity's pull between two distant worlds behaves exactly as his equations predicted, decade after decade, without so much as a hint of drift or exception. That kind of test matters more than it might seem. Even a deviation too small to affect anything built on Earth, a fraction of an inch out of place, would point toward entirely new laws of gravity and force a rewrite of more than a century of physics. After more than 50 years of watching, no such deviation has ever turned up. A pair of small mirrors set down in a few unhurried hours by two men in bulky white suits quietly became one of the most productive scientific instruments of the entire space age, still earning its keep more than half a century later. There is a particular kind of patience required for this sort of science, the kind that rarely makes headlines. Somewhere tonight, in the high desert of New Mexico or on a hillside above the French coast, an astronomer is almost certainly aiming a laser at a mirror that has not moved from its spot in the lunar dust since before that astronomer was born, adding one more data point, if the night cooperates, to a curve that will only reveal anything meaningful after being read alongside tens of thousands of others collected across half a century. It is not the kind of work that offers a dramatic discovery on any given evening. It offers something quieter instead, certainty, purchased one careful measurement at a time, night after night, for as long as anyone has been willing to keep watching. That measurement, repeated in this way for more than half a century, is what finally lets scientists check George Darwin's arithmetic against reality. And his arithmetic held. The mechanism he worked out, once you set aside the algebra, is not complicated to picture. The moon's gravity pulls on Earth's oceans, raising two low bulges of water, one on the side of Earth facing the moon, and one on the far side. If Earth did not spin, those bulges would sit in a perfectly straight line with the moon, and nothing further would happen. But Earth does spin, and it spins faster than the moon orbits, turning fully around once every 24 hours against the moon's 27 days. That faster spin drags the tidal bulges forward, slightly ahead of the moon's actual position overhead, before gravity and friction can pull them back into line. That small offset matters enormously. The forward bulge, sitting just ahead of the moon, tugs on the moon with its own gravity and nudges it forward along its orbit, the way a gentle hand on the back might speed someone already walking. A forward push on an orbiting body does not simply speed it up the way a push speeds up a car rolling down a road. It lifts the object into a slightly higher, slower orbit instead, farther from Earth's pull. That trade, height for speed, is not unique to the moon. Every satellite humanity has ever put into orbit obeys the same rule. Nudge something higher, and it settles into a slower, lazier path around whatever it circles. Nudge it lower, and it has to move faster just to keep from falling. The International Space Station, skimming along a few hundred miles above Earth, circles the planet in about 90 minutes precisely because it flies so low and so fast. The moon, thousands of times farther out, takes 27 days to make the same kind of trip, ambling rather than racing. Every time Earth's tides give the moon another small forward shove, they are not speeding it up in any way you would recognize from daily life. They are quietly promoting it to a slightly higher, slightly lazier orbit, 1.5 inches at a time, bit by bit, year by year. That forward tug from Earth's own tides is what carries the moon outward. And because energy in this exchange is neither created nor destroyed, whatever the moon gains, Earth gives up. Earth's rotation is slowing, almost imperceptibly, for the very same reason the moon is receding. They are really one fact, seen from two different directions, and the ocean tides that shape a coastline are, in the same quiet motion, reshaping the sky. So what does that mechanism add up to, in numbers a person can actually hold on to? 56 years of laser ranging have converged on a single, remarkably steady figure. The moon moves away from Earth by about 1.5 inches every year. Close to the distance, a fingernail grows in that same span of time. Sit with that comparison for a moment, because it is a strange one. Something as vast and ancient as the moon, a body large enough that its own gravity has held it perfectly round for 4.5 billion years, drifts outward each year by roughly the same distance as a sliver of keratin growing at the tip of your finger. Over the span of an average American lifetime, 80 years or so, that adds up to something like 10 feet of separation, about the height of a basketball hoop. Over the whole of recorded human history, every empire and treaty and photograph ever kept, the moon has eased outward by somewhere around 600 feet, not even the length of 2 football fields laid end to end. Since the day Armstrong and Aldrin left that first mirror behind in the dust, the moon has drifted a little more than 7 feet farther from Earth, roughly the height of a very tall man, spread out across 56 years of exquisitely careful measurement. What makes the number worth pausing on is not just its size, but its steadiness. When the laser ranging program began, the best measurements placed the Earth-Moon distance to within a few inches. Today, after 5.5 decades of refinement, that same distance is known to within about 1 millimeter, an improvement of something like 10,000-fold, and through all of that refinement, the recession rate has held remarkably close to the same figure, year after year. Darwin never lived to see his own equations confirmed, and even the astronauts who placed that first mirror on the lunar surface will never live to see the distance change by anything a human eye could detect. And yet the drift is there, patient and exact, written into the return time of a laser pulse fired from a quiet mountaintop in New Mexico toward a mirror sitting undisturbed in lunar dust. Observatories on more than one continent share their results, cross-checking each other's numbers, the way two people might separately balance the same checkbook. And, for more than half a century now, the totals have never meaningfully disagreed. It is worth saying plainly, though, that the number we measure today has not always been the number in force. 1.5 inches a year is what the Earth and Moon are doing right now, in this particular arrangement of oceans and continents. It has not been the same rate across the entire 4.5 billion years the two of them have shared, and it will not stay the same rate forever. That fact alone should tell you something. Whatever this drift has done to the Earth over the whole of its history is not a simple matter of multiplication. It is a far stranger story than that, one written into the rocks themselves, waiting to be read. Darwin proved it with a pencil. The Apollo astronauts proved it with a mirror, and neither proof, on its own, tells you the strangest part of this story. 1.5 inches a year is not really the story here. Multiplied across a single American lifetime, it is nothing. Multiplied across the whole of recorded human history, it is still barely more than a curiosity. Multiplied across 4.5 billion years, it becomes something else entirely, something that has already reached back into the rocks beneath your feet and reshaped the length of a single day, over and over, in ways stranger than a steady drift could ever explain on its own. 4.5 billion years is not really a number so much as it is an invitation, and there is no polite way to decline it. To understand what that kind of time truly does to a number this small, we have to go back much further than any human record, back to a version of Earth spinning so fast, and a moon hanging so close overhead that neither one would be recognizable to anyone watching tonight. To picture that version of Earth, you have to set aside almost everything familiar about the planet you know. There is no blue marble hanging serenely in the dark yet, no green continents, no white swirls of cloud. Go back 4.5 billion years to a solar system still cluttered with debris left over from its own birth, and you find a young, half-formed Earth sharing its orbit with a second, smaller world. Astronomers have given that world a name, borrowed from Greek mythology, Theia, after the Titan said to be the mother of Selene, the goddess of the moon. It is a fitting name, because Theia's entire purpose in this story, cosmically speaking, was to become the moon's mother in a far more literal and violent sense. Theia was roughly the size of Mars, large enough to count as a genuine planet in its own right, and for millions of years it seems to have orbited the young sun in roughly the same neighborhood as Earth, caught in one of the gravitationally stable regions that trail 60 degrees ahead of or behind a larger planet, the same kind of quiet cosmic parking spot that small asteroids still occupy along Jupiter's orbit today. The giant collision was not the first explanation scientists reached for. Long before Theia had a name, researchers had also proposed that the moon might simply have been a wandering body captured whole by Earth's gravity as it drifted past, or that Earth and the moon had formed side by side from the very same swirling cloud of dust and gas, like two pebbles collecting on opposite ends of the same riverbank. Both ideas eventually ran into trouble. A captured moon should show a chemistry entirely its own, shaped by wherever it had originally formed, and it does not. Two bodies forming side by side from identical material should share an identical mixture of heavier elements all the way through, and the moon, with its comparatively small and iron-poor core, plainly does not match Earth in that particular way either. Only the violence of a genuine collision, tearing material specifically from Earth's outer layers, rather than its iron-rich heart, explained both the similarities and the differences at once. Stability like that rarely lasts forever. In a young solar system still full of competing gravity, tugged at by every other half-formed planet nearby. At some point, in the earliest tens of millions of years after the solar system itself came together, Theia's orbit was nudged just enough to put it on a collision course with Earth. What followed was not a graze or a glancing scrape. Current evidence suggests something closer to a direct hit, planet striking planet, at a steep angle and tremendous speed, an event so violent it partially melted both worlds and blasted a cloud of vaporized and molten rock into orbit around what remained of Earth. Scientists did not simply guess at the timing of an event like this. They read it, patiently, out of the rocks themselves, using a kind of natural clock built into certain radioactive elements. One particular pairing, an element called hafnium slowly decaying into another called tungsten, ticks away at a fixed, known rate, and the ratio of the two, locked inside a rock sample, can reveal how long ago that rock last fully melted and separated into layers. The way a stopped clock still shows the exact moment it stopped ticking. That kind of dating only works because the collision itself was so thorough. A planet melting impact resets the clock cleanly, erasing whatever ratio existed before, and starting the count fresh from the moment the molten rock cools and solidifies again, which is precisely what makes the moon-forming collision so unusually easy to date compared to gentler, more gradual events in a planet's history. Applying that method to meteorites and to Earth and moon rock alike researchers have narrowed the giant collision to sometime within the solar system's first 100 million years, with much of the evidence favoring a date closer to its first 50. On the timeline of a 4.5 billion-year-old planet that places the Moon's violent birth astonishingly close to the very beginning of everything, that debris did not stay scattered for long, at least not on any geological timescale. Gravity pulled it back together into a ring circling the young Earth, and within that ring, chunks of rock began colliding and sticking to one another in the same basic process that built every planet in the solar system in the first place, just running at extraordinary speed. Some models suggest the bulk of the Moon came together in as little as a few hundred years, among the fastest planet-scale formation events proposed anywhere in the solar system, less time than the United States has existed as a nation. Other estimates stretch that timeline out further, but even the more cautious versions still measure the Moon's initial assembly in thousands of years rather than millions. Almost as soon as there was enough of it gathered together to call a moon, the newborn Moon was itself an ocean of molten rock, its surface glowing, slowly cooling and separating into layers, the way a cup of soup left standing will separate into fat and broth. The heavier ions sinking toward the center to form a small core, the lighter minerals rising to eventually harden into the crust that Apollo astronauts would one day walk on and collect samples from. Theia itself, meanwhile, never really left. Some researchers now suspect that not all of the impactor was blasted into orbit or destroyed outright. Deep inside Earth, roughly halfway to the center, sit two continent-sized blobs of unusually dense rock that seismic waves pass through more slowly than they do the surrounding mantle, features geologists have puzzled over for decades. One leading idea holds that those two buried provinces are not native Earth material at all, but the settled remains of Theia itself, folded into the planet's interior during the collision and resting there undisturbed ever since, a silent, mile-deep fossil of the very event that created the Moon. Earth came through the collision changed as well, and not only by gaining a companion. An impact violent enough to tear a moon's worth of material free from a planet does not leave that planet's spin untouched. Best estimates suggest the young Earth, in the aftermath, was rotating far faster than it does today, a day lasting somewhere in the neighborhood of 5 hours, sunrise to sunrise, about as long as a long doubleheader at a ballpark. Some of the more energetic collision scenarios researchers have modeled suggest it may have spun even faster still, a day of only 2 or 3 hours. Whatever the exact figure, the young Earth was, by any modern standard, spinning close to the edge of flying apart, whipped up by the same violence that gave it its moon. That fast-spinning Earth also had a much closer companion to keep it company. The newborn Moon is thought to have formed only a fraction of its current distance away, close enough that, had anyone been standing on Earth's surface to see it, it would have filled a vastly larger portion of the sky than the Moon does now, a pale, cratered giant looming overhead rather than the modest disk we are used to. Whatever oceans existed on that young, violent Earth would have answered to a gravity pull many times stronger than anything the Moon exerts today, tides rising and falling, not by a few feet along a shoreline, but by walls of water surging in and out on a rhythm far faster and far more forceful than any coastline has ever known since. A tide come and gone again in the time it now takes for a single, ordinary high tide to build. No shoreline from that era survives to describe it firsthand, but the physics leaves little room for doubt. The same nearby moon that would, eons later, rock quiet harbors gently twice a day was, at the very beginning, dragging entire seas back and forth in a matter of hours. It could not stay that close, though, and this is where the story returns to the same mechanism explored earlier tonight. The same tidal friction that is easing the moon outward by 1.5 inches a year today was already at work in those earliest chapters, only far more forcefully, because the moon was so much nearer, and the tidal bulges it raised in Earth's molten and, later, watery surface were correspondingly larger. The young Earth-Moon system did not drift apart slowly and gently. It uncoiled, at first, like a spring let loose, the moon retreating and Earth's spin slackening at a pace far swifter than anything happening in the sky above you tonight. None of this is guesswork dressed up as certainty. It is built from physical evidence, most of it gathered from the moon rocks themselves, and confirmed by tools scientists did not have available even a generation ago. But there is a second, entirely different kind of evidence for the ancient, fast-spinning Earth, and this evidence does not come from the moon at all. It comes from mud. Specifically, it comes from a peculiar kind of layered rock called a tidal rhythmite, formed in ancient tidal flats, where fine sediment settled out of the water twice a day, once with each incoming tide, leaving behind a wafer-thin band of silt each time. Over months and years, those bands stack up into a kind of natural ledger, not entirely unlike the growth rings inside a cut tree stump, except that a tree adds 1 ring per year, while a tidal flat can add hundreds of paper-thin layers in that same span, one for every single tide that ever rolled across it. Where geologists are fortunate enough to find a stretch of these rhythmites well preserved and undisturbed by later upheaval, they can do something remarkable. Count the bands the way you might count rings in a stump. Tally how many tidal cycles occurred in a single year and work backward from that count to the length of the day itself, since a faster spinning Earth packs more days and more tides into every trip around the sun. Simply counting layers is not enough on its own, though, and careful researchers do not stop there. A layer of ancient mud can be misleading, thinned or thickened by storms, or interrupted by gaps too subtle to notice by eye. To trust a reading, scientists cross-check it against the separate laws of celestial mechanics, the same equations that govern how the moon's orbit and Earth's spin must relate to one another at any given moment. If a rhythmite implies a certain number of days in a year and a certain number of lunar orbits in that same year, those two figures have to agree with each other according to physics, the way two different routes to the same address ought to produce the same distance. When the numbers from ancient mud and the numbers from orbital mechanics line up, as they have in the best preserved examples, geologists can trust the result with real confidence. When they do not, the rhythmite is set aside as unreliable, however tempting its raw numbers might otherwise be. A related method uses stromatolites, layered mounds built up over centuries by ancient mats of microorganisms, some of the very oldest visible evidence of life on this planet. Certain stromatolites grew in a rhythm, tied to the changing angle of the sun across the seasons, banding in a pattern that, again, can be read for clues about how many days made up a year in the distant past. Both methods share the same frustrating limitation. The right conditions for preserving this kind of record are rare. The rock has to survive undisturbed for an almost unthinkable span of time without being crushed, folded, or melted by everything a restless planet does to its own crust, and the results have to be checked and cross-checked before anyone can trust them. For long stretches of Earth's early history, geologists simply have no rhythmite or stromatolite record to read at all, only silence, whole hundreds of millions of years, for which no reliable clock has yet turned up anywhere on the planet's surface. One of the rare exceptions comes from a formation in Western Australia known as the Wheelie Wally. Tidal rhythmites laid down roughly 2.5 billion years ago in what was then a shallow, iron-rich sea, and somehow preserved ever since, through more than half the age of the planet, buried and undisturbed, while entire mountain ranges rose and eroded away above them. The rock itself is striped in fine, alternating bands of red and grey, iron-rich sediment laid down tide by tide across a coastline that vanished long before anything resembling a continent as we would recognize one had settled into place. Reading those ancient bands, geologists have calculated a day length at that time of somewhere between 17 and 19 hours, already more than double the blistering pace Earth spun at just after the moon-forming collision, but still a good 5 to 7 hours short of the day you are experiencing right now. Multiply that out, and a year in that distant era would have packed in something like 500 days, rather than the 365 you are used to counting off on a calendar, every one of them shorter, the sun rising and setting in a tighter, quicker rhythm than any human being would ever recognize as normal. From there, the story should, by all rights, continue in a straight line. Earth's spin should keep bleeding away, month after month, millennium after millennium, days slowly lengthening toward the 24 hours we take for granted, right up to the present. The month should have been lengthening right alongside it, for exactly the same reason. A moon easing outward takes longer to complete each orbit. The same way, a car on a wider racetrack needs more time to finish a single lap, even at a similar speed. Somewhere back in that ancient, close-orbiting era, a full circuit of the moon around the Earth, the very thing that now takes a bit over 27 days, may have taken only a handful of days from start to finish. For a long time, that straight-line picture of two numbers climbing steadily together, the day and the month both stretching out in lockstep, was more or less what scientists assumed, in the absence of any evidence to suggest otherwise. It turns out to be wrong, and the way it is wrong may be the strangest single fact in this entire story. Sometime around 2 billion years ago, not so terribly long in geological terms, after that Wheelie Wally snapshot, the lengthening of Earth's day appears to have simply stopped, not slowed, stopped, essentially dead in its tracks, holding at a day length somewhere close to 19.5 hours for a stretch of time that recent research places at roughly 1.5 billion years, all the way until around 600 million years ago. That conclusion did not come from a single team working alone. Researchers affiliated with the Chinese Academy of Sciences reached it by patiently reassembling the scattered geological record, one rhythmite and one stromatolite at a time, while a separate group at the University of Toronto arrived at very nearly the same billion-year standstill from an entirely different direction by modeling the physics of Earth's atmosphere directly. Two teams, working from two different kinds of evidence, converging within a matter of months of each other on the same extraordinary conclusion, is about as close as this sort of science ever comes to certainty. The stretch of time they had both stumbled onto already had a nickname among geologists. Coined years before anyone suspected, it also marked a billion-year pause in the length of the day itself, the boring billion. The name is not entirely fair to the era itself, even if it is fair to the pace of change. For most of that stretch, life on Earth remained almost exclusively single-celled, drifting in oceans that stayed remarkably stable in temperature and chemistry compared to the wilder swings before and after. The earliest cells with a proper nucleus, ancestors to every plant and animal that would eventually follow, appear to have arisen somewhere inside this same stretch of time, evolving with almost no urgency at all across hundreds of millions of years, as though waiting for some external signal to speed things along. Continents assembled into a supercontinent and drifted apart again with little fanfare. No towering ice sheets crept toward the equator the way they would in the dramatic global freezes, nicknamed Snowball Earth, that came both just before this stretch began and again after it finally ended. It was not a dead billion years, only a quiet one, a long-held breath between two much louder chapters of the planet's history. A billion years is longer than every animal that has ever lived, from the earliest simple sponges to the last blue whale, has existed on this planet combined. For the entire span of that billion years, whatever else was happening in the oceans and the thin, developing atmosphere above them, the day itself simply refused to grow any longer. The explanation for that pause did not come easily, and required scientists to look somewhere they had not thought to look before, not at the moon at all, but at the sun and at the air itself. Earth's oceans are not the only tides raised by another body's gravity. The atmosphere has its own tide, raised primarily by the sun rather than the moon, driven less by gravity directly and more by the daily rhythm of heating, as sunlight warms one side of the planet and lets the other cool. Ordinarily, that solar atmospheric tide is a minor, almost negligible player next to the ocean tides the moon raises, contributing only a faint whisper of extra push and pull compared to the moon's steady shove. But the strength of that atmospheric tide depends on temperature, and on how well its natural rhythm matches the length of the day itself. In much the same way, a glass hums loudest when you run a wet finger around its rim at exactly the right speed. 2 billion years ago, with a warmer atmosphere and a day already close to 19.5 hours, the solar atmospheric tide seems to have hit precisely that resonant note, growing strong enough to push back against Earth's spin in the opposite direction from the moon's pull, rather than simply adding to it. Picture two people pulling on opposite ends of the same length of rope, matched so evenly in strength that neither one budges an inch. That is roughly what happened to Earth's rotation for the better part of 1 billion years. The moon's ocean tides kept trying to slow the planet down, exactly as they always had and always would. The sun's atmospheric tide, tuned by pure coincidence to almost exactly the right pitch, pushed back just as hard in the other direction. Neither side could win. The length of the day held its ground, stuck at very nearly the same figure, while everything else about the planet, the shape of its continents, the chemistry of its oceans, the earliest slow stirrings of complex life, continued changing underneath that frozen clock. The timing of that billion-year pause turns out to matter for reasons that reach well beyond rotation itself. Two of the largest jumps in the oxygen content of Earth's atmosphere in the planet's entire history, bracket the boring billion on either side, one before it began and one after it finally ended, and researchers studying the stalled day length have pointed out an intriguing possible connection between the two. The earliest life capable of producing oxygen, simple photosynthetic organisms drifting in shallow water and coating the floors of ancient seas, could only manufacture the gas during the hours of actual daylight, and then only up to a point before their production leveled off for the day. In much the same way, a houseplant stops producing anything useful once the light in a room fades toward evening. A longer day means more hours of sunlight for that daily process to run, and more oxygen released before nightfall shuts it down. Some researchers now suspect that Earth's rise to the oxygen-rich atmosphere every animal on the planet depends on today had to wait, in part, for the day itself to grow long enough to give those ancient microorganisms the extra working hours they needed. It remains an open question, actively debated rather than settled, but it is a striking possibility all the same, that something as abstract as the resonant frequency of the atmosphere may have helped set the pace at which this planet slowly became breathable. Whatever finally ended the standoff between the sun's atmospheric tide and the moon's ocean tide, and researchers are still working out the precise trigger, the balance broke sometime around 600 million years ago. The atmosphere had been cooling gradually across that long billion-year stretch, and a cooler atmosphere carries a different resonant pitch, one no longer perfectly tuned to counter the moon's pull. Once that tuning slipped, the moon's tidal grip reasserted itself, and the day, after standing motionless for longer than most forms of complex life have existed, began lengthening again. It has been climbing ever since, through the rise of shelled sea creatures and the first fish and the first creatures to crawl onto dry land, through the age of the dinosaurs and every age that followed, up to the 24 hours you are living inside of tonight, with roughly 1 7/10 of a millisecond added to that number with each passing century, so slow a pace that not one single day in your entire life has ever felt 1 second longer than the last. Stop and consider for a moment everything that had to happen for the day to reach the length it has now. A planet had to be struck by another world entirely, violently enough to fling a moon into orbit and set the wreckage spinning at a pace of a handful of hours per day. That moon had to spend billions of years tugging at the oceans of its parent planet, slowing that furious spin down towards something more familiar. And then, almost as if the story paused to catch its breath, the whole process had to freeze in place for the better part of 1 billion years, held motionless by a coincidence of temperature and timing between the sun's warmth and the atmosphere's own rhythm, before finally continuing on to the 24 hours that now feel as permanent and unremarkable to you as the moon itself once did at the very beginning of tonight's story. The moon that caused all of this, the one currently sitting somewhere above the roof over your head, is still doing exactly what it has always done. It is still pulling on the oceans. It is still stealing a little of Earth's spin and carrying that stolen momentum outward into its own widening orbit. The billion-year pause is long over. The standoff between sun and moon broken for hundreds of millions of years now, and the day has been free to lengthen again this entire time, quietly, by fractions of a second, too small for any single lifetime to register. A 5-hour day, a frozen billion years at 19.5, a 24-hour day that took the whole of Earth's history to arrive at, and is still, this very night, not quite finished arriving, which raises the question this deep history has been building toward all along. If the moon's slow departure has already reshaped the length of a single day so many times, stretching it, then freezing it, then stretching it again, what does the road ahead actually look like? Not the deep past this time, but the calendar still to come, the specific, datable changes that this same slow drift is already carrying toward us, whether anyone down here happens to be watching or not. The calendar this story has been building toward does not begin with some distant, unimaginable future. It begins tonight, with the moon doing exactly what it has always done, and with a handful of consequences that scientists can already put real dates on. the way you might circle a day on a wall calendar rather than gesture vaguely at some future season. Some of those consequences are already, quietly, underway. The day is still lengthening. That part of the story never actually stopped, only paused for a stretch of time longer than complex life has existed, and it has been climbing again for the last 600 million years, adding roughly 1/7 of a millisecond to the length of a day with each passing century. That pace will continue, slow and unbroken, for as long as the moon keeps easing outward and Earth's oceans keep answering to its pull. Every so often, that slow lengthening even shows up in the official record books. Timekeepers who maintain the world's atomic clocks occasionally have to insert what is known as a leap second, an extra tick added to the year to keep humanity's precise, laboratory-grade sense of time lined up with the planet's own gradually slowing spin. A small bureaucratic footnote to a process that began 4.5 billion years ago, in a collision no one was alive to witness. It is a strange kind of honor for a committee of timekeepers to be, in effect, quietly chasing after a moon. The tides themselves are changing too, quietly, in step with the widening gap between the two worlds. Tidal force weakens rapidly with distance, falling off far faster than the moon's overall pull on Earth as a whole. So, even a small increase in the Earth-Moon distance chips away disproportionately at the strength of the tides a coastline actually feels. A harbor that floods and drains with real force today will, over a long enough stretch of deep time, answer to a gentler and gentler hand, the tide still coming and going twice a day, only with less conviction behind it, the wake of a system slowly loosening its grip. Fishermen who plan their mornings around the tide charts, and the coastal marshes that depend on a strong daily flush of seawater to stay healthy, are quietly, almost imperceptibly, living through the early edge of that same long unwinding. Entire coastal ecosystems, from the mudflats where shorebirds feed at low tide to the salt marshes that filter and nourish the water flowing back out to sea, have spent their entire evolutionary history calibrated to a tidal rhythm that has never, once, in all of that time, held perfectly still. Nowhere does that loosening grip show up more clearly or more suddenly than in the sky itself, in an event most people have only ever seen described as an act of perfect cosmic coincidence, a total solar eclipse. You likely already know the basic arrangement. The sun is enormous, roughly 400 times wider than the moon, and also, by happy accident, roughly 400 times farther away, so that the two objects appear to be almost exactly the same size, hanging in Earth's sky. When the moon slides directly between Earth and the sun, it can, under the right circumstances, cover the sun's blazing disk so precisely that only the pale, feathery corona remains visible around the edges. Day turning briefly to twilight in the middle of the afternoon. Birds have been known to fall silent and return to their roosts. The temperature can drop noticeably in the space of a few minutes. Bright stars and planets, ordinarily invisible in daylight, appear scattered across a sky gone suddenly dark. It is, by every account of those who have stood inside the path of one, unlike any other natural event on Earth. What far fewer people realize is how narrow those right circumstances actually are, and how much narrower they are quietly becoming. The moon's orbit around Earth is not a perfect circle. It is a gentle oval, close enough to round that you would never notice the difference by eye, but real enough to matter enormously for an event as finely balanced as an eclipse. At its closest approach, called perigee, the Moon sits somewhere around 221,000 miles from Earth. At its farthest, called apogee, that distance stretches to roughly 252,000 miles, a difference of about 13%, small on paper, but large enough to noticeably change how big the Moon appears against the Sun. Averaged across its entire orbit, the Moon today actually appears very slightly smaller than the Sun by a little more than 2%, which means that most solar eclipses happening on Earth right now, something like 6 out of every 10, are not total eclipses at all. They are annular eclipses, the ones skywatchers call a ring of fire, where the Moon sits too far out to fully cover the Sun's disk, leaving a bright, unbroken circle of sunlight glowing around its silhouette. Only when a solar eclipse happens to line up with the Moon nearer to perigee, closer than its average distance, does the Moon appear just barely large enough to swallow the Sun completely and produce true totality, that brief, remarkable darkness that has drawn travelers across entire continents to stand in its path. Anyone curious enough to see the difference for themselves will not have to wait long. A ring of fire annular eclipse is due to sweep across parts of the world within the next couple of years, visible without any special travel for a great many people, while astronomers have already calculated, centuries in advance, that one especially favorable total eclipse in the year 2186, with the Moon unusually close to perigee, will produce nearly 7.5 minutes of darkness over parts of South America, longer than almost any total eclipse in recorded history. Totality, in other words, is not the ordinary outcome of a solar eclipse today. It is already the exception, made possible only because the Moon's orbit still occasionally brings it close enough. And that margin, the thin cushion between just barely close enough and not quite close enough anymore, is exactly what 1.5 inches of yearly recession is spending, one solar eclipse at a time. Cultures across human history, long before anyone understood perigee or apogee or the mechanics of an orbit, treated a total eclipse as something closer to an omen than an astronomical event, and it is not hard to understand why. Ancient chroniclers in China described dragons attempting to devour the Sun, and the imperial court is said to have kept court astronomers on staff specifically to predict and, when necessary, ceremonially ward off such an event. Other cultures across the ancient world independently arrived at strikingly similar stories, a great beast or spirit swallowing daylight itself, only to release it again minutes later. The same basic fear, expressed in dozens of unrelated languages, by people who had no way of comparing notes with one another. Only gradually, as careful record-keeping accumulated across centuries of watching the sky, did astronomers begin to notice the underlying pattern, that the Sun always returned, that the timing followed rules, that the event could, with enough patience, be predicted rather than merely feared. That transformation, from omen to orbital mechanics, took the better part of human civilization to complete, unfolding across thousands of years of patient, largely anonymous record-keeping long before anyone had a telescope, let alone a spacecraft. And, it is worth remembering, sitting here tonight with a number as precise as 600 million years in hand, just how recently in that same civilization anyone gained the tools to calculate an ending this far off with any confidence at all. The mathematics of it are not complicated, even if the timescale is almost impossible to hold in your head. As the Moon's average distance from Earth continues to grow, both its closest approach and its farthest gradually shift outward together, like two ends of the same stretching rubber band. Eventually, the moon's closest possible approach to Earth, its perigee, will itself have grown too distant to produce a total eclipse under any circumstances at all. Even on the most favorable night of the most favorable year, NASA scientists have calculated the threshold precisely. Once the moon's orbit has widened by roughly 14,600 miles beyond where it sits tonight, total solar eclipses will end permanently. At the current, steady rate of about 1.5 inches a year, reaching that threshold will take a little over 600 million years. It is worth sitting with how strange that number actually is. 600 million years ago, nothing resembling an animal with a backbone existed anywhere on Earth. The most complex life in the oceans consisted of soft-bodied creatures that would not be recognizable as anything alive to a casual observer today. Drifting shapes with no shells, no eyes, nothing a person standing on that ancient shoreline could have pointed to and called a face. Run that same span of time forward from tonight, and you arrive at the moment the last total solar eclipse ever visible from Earth quietly comes and goes, likely without a single witness who understands what they are watching disappear for good. Everyone alive today, and every human being who will ever live across the remaining 600 million years of total eclipses still to come, is watching from inside a genuinely temporary, genuinely rare, astronomical window, one that a great many worlds, at a great many points in their history, never get to open at all. That number, 600 million years, deserves one honest caveat, the same kind of caveat that applies to nearly every deep time prediction in this story. It assumes the moon keeps receding at exactly today's rate, in a straight, unbroken line, for the next 600 million years. Recession does not actually work that way, and this story has already touched on why. It depends on the size, shape, and arrangement of Earth's ocean basins, on how efficiently they happen to slosh in resonance with the tidal rhythm passing through them, and those basins are anything but fixed. Continents drift. Oceans widen, narrow, and occasionally close altogether, reshuffling the very geography that determines how hard the tides can grip the moon and pull it outward. The Atlantic Ocean today happens to sit at close to the ideal width for amplifying that tidal grip, part of why the modern rate of 1.5 inches a year runs faster than the average pace across most of Earth history. Some researchers who study this question believe the current rate could slow considerably as the continents keep rearranging themselves over the coming hundreds of millions of years, which would push the true end of total solar eclipses out considerably further, by some estimates, past 3 billion years from tonight, rather than 600 million. Either way, sooner or later, on a timeline no human civilization will ever witness in full, the particular kind of daytime darkness that has awed every sky-watching culture in human history will end, quietly, without ceremony, the last total eclipse differing from every ordinary annular one before it, only in the fact that no one will get another chance. There is a second inheritance from the moon, quieter than eclipses and far less visible, that carries its own kind of expiration date, and it has nothing to do with tides or daylight at all. It has to do with the simple fact that Earth does not spin perfectly upright. Tilt your head very slightly to one side and hold it there. That, roughly, is the position Earth's axis has held relative to the flat plane of its orbit around the Sun for as long as complex life has existed, a lean of a little over 23 degrees, responsible for the entire rhythm of the seasons. Without that tilt, there would be no summer and no winter anywhere on the planet, only an endless, unchanging middle season repeating at every latitude, year after year, the sun tracing the same unvarying arc across the sky every single day of the calendar. With too much tilt, seasons would swing to violent extremes, poles baking under continuous summer sun for months before plunging into equally prolonged winter darkness, and the temperate middle latitudes, where most people on Earth actually live, would lurch between the two far more sharply than they do now. Earth, as it happens, sits in a comfortable, moderate range, and has sat there for a very long time, gently rocking back and forth between about 22 and a tenth degrees and 24.5 degrees over a cycle that repeats roughly every 41,000 years, never straying much further in either direction. That is not the only slow motion Earth's axis makes. The axis itself also traces out a slow circle in the sky, the way the handle of a spinning top traces a lazy loop before the top finally topples over, without the lean itself changing at all, only the direction it points. Right now, that axis happens to point almost exactly at a modest, unremarkable star known as Polaris, the very star sailors and farmers throughout history relied on to find true north on a clear night. That alignment is not permanent. The circle Earth's axis traces takes roughly 26,000 years to complete, and thousands of years from now, the axis will have wandered far enough that Polaris will no longer sit anywhere near true north at all, replaced eventually by other stars along that same slow circuit, a fact the ancient Egyptians, who oriented their pyramids using an entirely different pole star than the one sailors would later rely on, would have found unsurprising. That stability is not an accident, and it is not guaranteed. A fast spinning top holds its lean with real stubbornness, resisting anything that tries to tip it further. A slow, wobbly top is far easier to knock off balance entirely. Earth's own wobble is kept moving at a brisk, stabilizing pace almost entirely because of the Moon's gravity tugging on the bulge around Earth's equator, a bulge caused by the planet's own rotation. Remove the Moon from that equation, and calculations, first published by a team of French astronomers in 1993, suggested something startling. Earth's wobble would slow down enough to fall into step with a much larger, far more disruptive rhythm elsewhere in the solar system, one connected to the slow drift of the other planets' orbits, and once caught in that larger rhythm, the tilt of a moonless Earth could swing wildly, potentially anywhere, from nearly no tilt at all up to something like 85 degrees, a lean so extreme the planet would spend stretches of its year essentially lying on its side, not unlike Uranus does today, rolling around the sun almost like a ball, rather than spinning upright like a top, its own peculiar tilt, likely the result of an ancient collision, not entirely unlike the one that gave Earth its moon in the first place. That original calculation, striking as it was, has not gone entirely unchallenged. It came from a team led by the French astronomer Jacques Lascar, working with the computing power available in the early 1990s, machines that look almost quaint by today's standards but were, at the time, capable of running the kind of long, patient, orbital simulation this question demands. A later team, working with considerably more computing power roughly 2 decades afterward, ran the same basic question and found the picture somewhat less dramatic than first proposed, suggesting a moonless Earth's tilt might wander only some 10 degrees beyond its current range, rather than swinging all the way to 85, a genuine scientific disagreement that remains only partly settled, the kind of honest back and forth that happens whenever better tools get pointed at an old, hard question. Mars, meanwhile, offers something closer to a real-world demonstration rather than a simulation. The red planet has two moons of its own, Phobos and Deimos, but both are little more than captured rubble. Asteroids barely a few miles across, far too small to exert any meaningful stabilizing pull. More like pebbles caught in orbit than proper moons. Mars's tilt, as a result, is known to have wandered considerably over its history, and calculations suggest it continues to do so today, swinging through a much wider range than Earth ever has. A nearby, observable hint at what an unprotected planet's tilt can actually do given enough time. What both teams studying Earth's own case agree on, and what no one seriously disputes, is the underlying principle. The moon's gravity measurably steadies Earth's tilt, keeping the planet's seasons predictable and its climate, across the scale of tens of thousands of years, considerably calmer than it would otherwise be. Ice ages themselves are believed to march to the rhythm of exactly this kind of slow, orbital, and axial motion. The tilt and wobble and shape of Earth's orbit, combining over cycles of tens of thousands of years to nudge sunlight around the globe in patterns that either encourage or discourage vast sheets of ice from creeping down out of the polar regions. A wilder, less predictable tilt would scramble that rhythm considerably, and with it, the far slower rhythm of ice ages and warm periods that has shaped so much of the landscape you would recognize on a map of the modern world. Here is where the story folds back on itself, in a way that even many astronomers find unsettling. The moon currently provides that stabilizing service. It will not always be close enough to keep providing it. As the moon recedes, inch by inch, year after year, its gravitational grip on Earth's equatorial bulge weakens along with everything else it touches, and the pace of Earth's wobble will gradually slow down right alongside it, exactly the mechanism that, in a moonless world, was calculated to invite chaos in the first place. The moon is not, in other words, a fixed shield that either exists or does not. Its protection is a matter of degree, tied directly to how close it happens to be sitting at any given moment in its long outward journey. And that journey, this story has already made clear, has no stopping point in sight. Researchers modeling the long-term evolution of the Earth-Moon system have found that this slowing wobble could, all on its own, eventually carry Earth's rotation into that same disruptive resonance the earlier calculations described. The tilt potentially swinging as far as 80 degrees or more, on a timeline current estimates place somewhere between 1.5 and 4.5 billion years from tonight, with the first real excursions possible within about 6 billion years, even under more conservative assumptions. The moon, in this telling, is less a permanent guardian of Earth's stable seasons, and more a temporary one, doing its job only for as long as it stays close enough to keep the wobble moving at a stabilizing pace, and every inch of its slow departure edges that particular kind of protection a little closer to running out. It is worth being precise about what this does and does not mean, since a claim this large is easy to overstate. This is not a prediction that Earth's tilt will destabilize on any specific date, the way the end of total eclipses can be dated. It is a modeled possibility, built on assumptions about how the Earth-Moon system continues to evolve over spans of time longer than almost anything else discussed tonight. And like any model reaching that far into the future, it carries real uncertainty alongside its real physics. What makes it worth including in this story at all is not certainty, but plausibility. A serious, published calculation built by scientists working through the same equations that correctly predicted the moon's recession in the first place, suggesting that the very stability we take as one of Earth's most basic, dependable features has, quietly, an expiration date of its own, tied to the same slow drift responsible for everything else examined tonight. Picture, for a moment, what a wilder tilt would actually mean for anyone standing on the ground to watch it unfold, not as an abstract number on a chart, but as a season. A backyard, in a temperate state that currently sees a mild, predictable autumn, might instead swing toward a summer so long and so severe that rivers run low for months on end, gardens scorched well past the point any gardener today would recognize as normal, followed by a winter arriving late and leaving reluctantly, ice lingering deep into a calendar month that used to belong to spring. Regions near the poles, tilted more steeply toward and away from the sun in turn, might spend the better part of a year in unbroken daylight, followed by the better part of a year in unbroken dark, a pattern already familiar at the poles today in a modest form, stretched out to an extreme no place on Earth currently experiences. None of this would happen suddenly, in the space of a single human generation. It would creep in over tens of thousands of years, exactly the kind of slow reshaping that this entire story has been circling around from its very first sentence. Stack these two threads up against each other, and a pattern starts to emerge that the deep past, for all its strangeness, never quite prepared you for. The eclipses end first, on a timescale measured in the hundreds of millions of years, an ending near enough, in cosmic terms, that scientists can name an actual number for it with real confidence, backed by orbital mechanics as reliable as anything in astronomy. The tilt of the entire planet potentially destabilizes sometime after that, on a timescale stretching into the billions, a slower fuse attached to a far larger and far less certain outcome, one still being actively debated by the very researchers who study it. Both threads trace back to the exact same cause, a moon that has never once, in 4.5 billion years, stopped easing outward and shows no sign of stopping now. Both threads, too, share something else in common. Neither one describes the moon vanishing. Both describe something quieter and, in a way, more interesting. The moon staying exactly where physics says it must be at each stage of its long departure, while everything downstream of its presence, the sky's rarest spectacle, the planet's own steady lean, slowly, unhurriedly, adjusts to how far away it has become. Nothing about either thread requires the moon to disappear. Both simply require it to keep doing what it has already been doing, patiently, for longer than anything else discussed tonight. Which brings this story, at last, to the one ending it has not yet actually confronted directly, the ending implied from the very first line of tonight's title. Everything examined so far, the eclipses, the tilt, the tides, the length of a single day, has been a story of things slowly changing, weakening, or running out, each one anchored to a real, calculable point, somewhere on the calendar of deep time. But the title of tonight's story promises something more absolute than a weakened tide or a lost eclipse. It promises an ending to the moon itself, the thing disappearing entirely, rather than simply drifting farther off. That claim deserves the same honest treatment as everything that came before it, no more exaggerated and no less carefully examined, and it turns out to lead somewhere far stranger and far more revealing than the straightforward vanishing act the title seems to describe. A genuine ending, just not the one anyone watching tonight was likely expecting. That's the full 4-part script in order. 1, 2, 3, 4. Everything you need is in the chat now. Every physical process has, in principle, a finish line, some final configuration it is quietly working toward, even if nothing alive will ever stand there to watch it arrive. Tidal friction is no exception. There is, in fact, a genuine, calculable endpoint to the moon's long recession, a true final chapter to the story this entire evening has been tracing back to its beginning. One this evening owes its listener before the night is through. It is worth describing honestly, in full, because it is the only ending this particular physical process actually has, and because a story that promised an ending owes its listener the real one, whatever shape it turns out to take. It is also, as you are about to hear, not the ending anyone watching tonight needs to worry about. If nothing else in the solar system ever intervened, the moon's outward drift would not continue forever. It would eventually stop, arriving at a state astronomers call mutual tidal lock, the same condition that already exists, right now, between two much smaller worlds far out at the edge of the solar system. Pluto and its largest moon, Charon, reached that state long ago. Charon was found almost by accident in the summer of 1978, when an astronomer at the United States Naval Observatory named James Christie noticed something odd in a set of photographic plates he was examining, taken with a telescope in Flagstaff, Arizona. He was not looking for a moon at all. He was simply trying to refine Pluto's orbit around the Sun, tightening up decades-old calculations using better images. Pluto, in those plates, looked subtly elongated, as if it had grown a small bump on one side, and the direction of that bump shifted back and forth on a steady rhythm as the days passed. Christie had stumbled onto Pluto's only large moon, hiding in plain sight in images astronomers had been studying for years without noticing it. A discovery that would eventually reveal Pluto and Charon to be one of the strangest partnerships in the entire solar system. That moon does not rise and does not set from Pluto's surface. It simply hangs there, fixed in the sky above one hemisphere of Pluto, forever, while the opposite hemisphere never sees it at all. Not once, not ever. Pluto shows the same courtesy back. The same face of that small, icy world is permanently turned toward Charon, and the same face of Charon is permanently turned toward Pluto, two worlds locked in a silent, unmoving stare that has already lasted longer than complex life has existed on Earth and will continue for as long as the two of them remain in orbit together. That is what full tidal lock actually looks like. Not a metaphor, but an existing place. In this solar system, you could point a telescope at tonight, a genuine preview of the Earth-Moon system's own theoretical destination, already sitting out past Neptune for anyone patient enough to look. And it is, in principle, where Earth and its own moon are headed. If the moon kept receding at a steady pace, and Earth's spin kept slowing to match, the two would eventually reach the same kind of standoff. Earth's day would stretch out to match the moon's orbital month, and the month itself would keep stretching right alongside it, both of them climbing together toward a single shared number. Calculations suggest that final, matched length would settle at something like 47 of today's days, an Earth day and an Earth month, each one nearly 2 months long by the calendar you know, arriving together in lockstep, because they would, at that point, be the very same rotation viewed from two different directions. The moon would need to drift out to something like a third again farther than its current distance to get there, and once it arrived, the outward creep, the 1.5 inches every year that opened this evening's story, would finally, genuinely stop. Researchers who have modeled that process put the timescale required at something on the order of 50 billion years, a figure so far beyond anything discussed so far tonight that it barely even qualifies as a prediction in any ordinary sense. More, a statement about where the underlying mathematics would eventually lead if left alone, undisturbed, for a span of time longer than the universe itself has existed up to this point. Picture what a night sky would look like under those conditions. From one half of the Earth, the moon would hang fixed in place, never rising, never setting, a permanent fixture in one particular patch of sky, exactly as Charon hangs over Pluto tonight, visible from a bedroom window at every single hour of every single day for the entire span of a lifetime. Whole cultures on that half of the world would grow up never having seen the moon move at all, a single unblinking companion parked in one specific corner of the heavens for the entire span of every life ever lived there, its phases still shifting slowly from full to new and back again, but its position in the sky never changing by so much as a hair's width. From the other half of the planet, the moon would never appear at all, not once, not glimpsed at the horizon, not rumored about by travelers. An entire hemisphere of Earth living out its whole existence beneath a sky that had, as far as anyone there could ever know, no moon in it whatsoever, a blank patch of stars where a companion used to be for the other half of their own world. It is a genuinely strange image, worth sitting with for a moment before setting it back down, and it is also, this story now has to admit, not one that is ever actually going to happen. The reason has nothing to do with the moon and nothing to do with Earth's oceans or its spin or its tilt. It has to do with the sun. The sun you see in the sky tonight is, in the language astronomers use, a fairly ordinary, middle-aged star, roughly 4.5 billion years old, currently in the long, stable phase of its life, where it converts hydrogen into helium deep in its core at a steady, reliable rate. That stability is not permanent, and it is not even particularly slow to end, not on the scale of billions of years this evening has already spent getting comfortable with. Stars like the sun grow brighter as they age, gradually, the way a bed of coals grows hotter as more fuel settles and compresses beneath it, and that brightening has real consequences for a small, water-covered planet orbiting at a very particular, very precise distance away. Within roughly the next billion years, astronomers calculate the sun's steady brightening, an increase of something like 10% in overall output, will have pushed its habitable zone, the narrow band of distance where a planet's surface can hold liquid water, outward past Earth's orbit entirely. Once that happens, Earth's oceans will begin to boil away in earnest. The process is not expected to be sudden or dramatic in the way a pot boiling over on a stove is sudden. It unfolds instead as a slow, self-reinforcing spiral, playing out over hundreds of millions of years rather than any span a person could watch unfold. Warmer oceans send more water vapor into the atmosphere. That added vapor traps still more heat. The added heat evaporates. Still more water, each step feeding the next. High in the atmosphere, sunlight begins breaking apart the water molecules that have drifted up there, splitting them into hydrogen and oxygen, and the lightest of those fragments, the hydrogen, simply drifts off into space and is lost for good, carried away a molecule at a time by a process with no way to run in reverse. What began as gradual heating ends over the following few 100 million years, with an entire ocean's worth of water gone, not evaporated and rained back down the way a summer drought ends, but genuinely, permanently removed from the planet, boiled away, and stripped into space, one broken molecule at a time. A scorched, waterless world where a blue and green planet used to be is what remains. That single billion-year mark, not any far more distant event, is the real deadline this solar system has quietly set for a living Earth, arriving well over 100 times sooner than the theoretical tidal lock this evening described only a few minutes ago. The Sun's own story does not stop there, either. Roughly 5 billion years from tonight, having spent the vast majority of its available hydrogen, the Sun will leave the stable, middle-aged phase of its life behind entirely. Its core, no longer able to sustain the fusion that has held it in balance for billions of years, will begin to contract, and as it does, the Sun's outer layers will respond by doing something dramatic, swelling outward, engorged and reddened, into what astronomers call a red giant. Over the next couple of billion years after that, the transformation accelerates. The Sun's visible surface will cool as it expands, taking on a deep, smoldering red color in place of the familiar yellow-white glow it shows tonight. Even as the star as a whole grows to a size that defies easy comparison, its outer edge, eventually reaching outward to somewhere in the neighborhood of where Earth's orbit sits today. Anyone able to witness it safely from a distant vantage point would see something almost impossible to reconcile with the small, steady disk overhead tonight, a bloated, ember-colored sphere swallowing an ever larger portion of the sky, dim enough at its reddened surface to look at almost directly, yet so enormous that its outer atmosphere alone would dwarf the orbit every inner planet currently occupies. Mercury and Venus, the two planets closer to the Sun than Earth, will almost certainly be swallowed whole during this expansion, their surfaces consumed by the same stellar material that once quietly warmed them from a comfortable distance. Whatever remained of their cratered, airless surfaces, vaporizing into the thin outer atmosphere of the star that made them. Earth's own fate during that final swelling is the one detail modern astronomy has not fully settled, and the honest answer deserves to be given as the genuine scientific uncertainty it actually is, rather than as false confidence in either direction. As the Sun sheds mass during this transformation, streaming material outward into space, its gravitational grip on the remaining planets weakens slightly, nudging their orbits a little farther outward over time. A small mercy that some early calculations hoped might be enough to spare Earth from outright engulfment entirely. More detailed, more recent modeling, working through the physics of both that orbital drift and the physical drag Earth would experience plowing through the Sun's thin outer atmosphere as the two draw close, has reached a more sobering conclusion. Published in a peer-reviewed astronomy journal after careful step-by-step simulation of both effects together, Earth most likely does not escape. Somewhere around 7.5 billion years from tonight, by the most careful estimates currently available, the expanding Sun very probably overtakes Earth's orbit entirely, and whatever scorched, lifeless remnant of this planet still exists by that point is drawn inward, its orbit decaying as it plows through increasingly dense stellar gas, until it is consumed along with Mercury and Venus, three small, rocky worlds, absorbed one after another into the outer layers of the star that raised them all from the same original cloud of dust. A small minority of models leave open a narrow chance that Earth's orbit gets pushed out just far enough to survive as a bare, blackened rock, orbiting within the Sun's own bloated outer layers, rather than being swallowed by them entirely. Either way, whether Earth is consumed outright or merely left circling inside the wreckage of what used to be comfortable daylight, nothing resembling the living world you know continues to exist by that point, and it has not existed for billions of years already, not since the oceans first boiled away. There is, oddly enough, a brief, strange consolation tucked inside this otherwise sobering timeline, and it belongs in this story precisely because it is true, not because it softens anything that came before it, and not because this evening owes anyone a silver lining before it closes. As the Sun's habitable zone sweeps outward during that long, final expansion, it will, for a few 100 million years, pass directly through the outer solar system, over worlds that have spent the whole of their existence as frozen, distant curiosities. Saturn's moon Titan, already wrapped in a thick, hazy atmosphere unlike any other moon in the solar system, could find itself briefly warm enough to host lakes of liquid water rather than the frigid liquid methane that fills its lakes today, its orange smog perhaps thinning, for a geological instant, into something almost inviting. Farther out, still, distant Pluto and its companion Charon, that same permanently locked pair described a few minutes ago, could see surface temperatures climb to something almost temperate. The deep, ancient ice covering both worlds, finally softening after more than 4 billion years, locked in permanent, bone-deep cold. None of it lasts. The Sun continues its transformation, regardless of what it briefly warms on the way, and within a few 100 million years, every one of those newly thawed worlds cools again as the Sun sheds its outer layers entirely and settles into its own final, quiet form, a small, dense ember called a white dwarf, no larger than Earth despite containing most of the Sun's original mass, radiating away the last of its heat for longer than the universe has existed up to this point, a slow fade, with no true endpoint of its own, simply growing dimmer and dimmer across a timescale that makes even tonight's billions look modest by comparison. Set that entire timeline, the boiled oceans, the red giant, the very likely engulfment, alongside the 50 billion years or so that full tidal lock between Earth and the Moon was calculated to require, and the shape of the true ending becomes impossible to miss, however you choose to look at it. The Sun's transformation arrives first, by a wide margin, roughly 6 or 7 times sooner than the Moon and Earth could ever have finished their slow, patient dance regardless, and that is measuring generously. From the moment the Sun finally leaves the main sequence, rather than from the much earlier point, a billion years from now, when the oceans are already gone, and nothing resembling this evening's audience could possibly still be here to notice anything at all. The tidal lock this evening described in such detail, the fixed moon hanging motionless over half an Earth and utterly invisible from the other half, is not a false idea. The mathematics behind it are sound, the same mathematics George Darwin worked out with nothing but tidal tables and patience, the same mathematics the Apollo astronauts' small mirrors confirmed to a fraction of an inch. It is simply an ending that the Earth-Moon system will never actually live long enough to reach, because a different, far larger story, one that has nothing to do with either of them individually, arrives first and closes the book before that particular final page is ever turned. This is, in the end, the honest answer to the question this evening opened with. back when the moon still felt like the one truly fixed point in an otherwise restless sky. The moon is not leaving. Not in the sense the word usually carries, not in the sense of a door closing, a light going out, a companion walking off towards some particular, nameable horizon. The moon is doing something stranger than leaving. It is receding, patiently, measurably, by about 1.5 inches, with every turn of the calendar, exactly as it has for 4.5 billion years, exactly as it will for every year still to come, all the way up until something else entirely. A star, swelling in on itself, long after any human concern could possibly still apply, ends the conversation on its own terms. Think back, for a moment, to where this evening actually began. Somewhere above the roof, over your head, tonight sits the very same moon that felt, at the very start of this story, like the one truly permanent fixture in an otherwise restless sky. The thing that had watched every generation of your own family come and go without ever once seeming to change even slightly. That feeling was not foolish. It was simply built on a mismatch of scale, so enormous that no human mind, no human lifetime, no stretch of human civilization has ever been long enough to notice the alternative. George Darwin spent a career proving, with a pencil and borrowed tidal records from 14 ports, that the moon must be moving. He never once got to see it move. The astronomers who have spent 56 years bouncing laser light off a mirror in the dust of the Sea of Tranquility have never seen it move either, not with their own eyes, only in the patient arithmetic of a number too small for any human sense to register directly. The moon has been leaving. In that sense, this entire time, through the whole of this story, and through the whole of your own life, and through every life that came before yours, and it will keep on leaving in exactly that same quiet, undetectable way, long after there is anyone left on this particular planet to notice. Every thread this evening followed turns out, on reflection, to be telling some version of the same story, viewed from a slightly different angle each time. The way a single melody can sound entirely different depending on which instrument happens to be carrying it. A day that stretched from a few violent hours into the 24 steady ones you know, except for a billion-year stretch in the middle when it simply refused to move at all, held motionless by a coincidence between sunlight and air that nobody could have predicted in advance. A sky that will, on a schedule already calculated to the century, someday stop producing the one kind of daytime darkness every human culture has ever found reason to fear or celebrate. A darkness ancient astronomers once blamed on dragons and spirits before anyone understood. It was simply geometry, patient and indifferent, playing out on schedule. A planet's own gentle lean, the very thing responsible for spring turning to summer, and summer fading back into autumn, quietly borrowed, for now, from a stability that has its own expiration date written into the same physics that explains everything else examined tonight. None of these were separate stories being told back to back. They were the same slow mechanism, examined at 4 different distances, the way a single object looks different depending on whether you are standing close enough to touch it or far enough away to lose sight of it in the haze. The underlying shape never actually changing, only your vantage point on it. There is a particular kind of vertigo that comes from holding a timescale like this one in your head for more than a few minutes at a time, and it is worth naming honestly rather than rushing past it. The way a person might name a strange feeling out loud, simply to make it easier to sit with, easier to carry back out into an ordinary evening once the story itself has finished. 600 million years, the point at which the last total eclipse comes and goes, is a number so large that it renders the entire span of human civilization, every pyramid and every symphony and every war ever fought, a rounding error too small to register. And yet, 600 million years is, itself, a rounding error against the timeline this story has spent its final minutes describing, dwarfed many times over by the billions of years standing between tonight and the sun's own transformation. Numbers this size do not actually get easier to understand the more of them you stack together. If anything, they get harder, each new billion sliding past the one before it with the same numb, unmemorable weight, the mind reaching for some familiar handhold and finding none large enough to hold onto. Perhaps that difficulty is, itself, the most honest thing this story has to offer. Not a lesson, exactly, and not a warning, but an accurate description of the size of the thing you have spent this evening quietly considering. Human beings are built, by every measure that matters, for a much smaller kind of time, the length of a season, the span of a single life, at the very outer edge, the handful of centuries a family name might survive being spoken aloud, a name carved into a headstone that will itself have worn illegible long before even the shortest of tonight's numbers has finished counting down. Nothing in that inheritance prepares anyone to genuinely feel the weight of a billion years, let alone 7 or 8 of them stacked one atop another. And no amount of careful narration this evening could have changed that fact. What careful narration can do, and what this evening has tried to do throughout, is simply tell the truth about the numbers as best as they are currently understood, without inflating them for effect, and without shrinking them for comfort, and let the vertigo be whatever it naturally turns out to be. That is not a tragedy, and it is not a triumph either. It is simply what is actually happening, described as plainly and as carefully as an evening like this one can manage, the way any honest storyteller ought to leave a listener at the end of a long night. The day you are living inside of tonight took the entire history of the Earth to arrive at, including a billion years when it refused to grow any longer at all, held in place by an accident of temperature and timing between the sun's warmth and the air itself. The eclipses you may someday stand beneath, or may have already stood beneath, are borrowed time on a clock that started running the moment a Mars-sized world struck the young Earth and never once stopped since. The steady, unremarkable tilt that gives you spring and autumn rather than an endless, unchanging season is a gift with a use-by date measured in billions of years rather than an inheritance with no strings attached. And the ending promised at the very start of this story, the one this evening has spent its entire length walking toward, turns out not to be an ending for the moon at all, but a story about how some endings simply never arrive in the shape you expected them to, overtaken instead by something larger, something that was never really about the moon in the first place, something that will finish its own business long after the last question this evening raised has stopped mattering to anyone at all. You will not see any of this happen. Neither will anyone you will ever meet, or anyone their children will ever meet, or anyone descended from them 1,000 generations on. And that, more than anything else uncovered this evening, may be the truest thing this story has to offer, that you are living tonight inside the opening pages of a story so vast it does not need an audience to keep unfolding, one small, patient inch at a time, whether or not anyone is left to watch it, whether or not anyone ever fully understood, the way you now do, what was quietly happening the entire time, above every roof, on every night, since long before there were roofs at all. Sleep now. The moon drifts on tonight, patient, unhurried, and utterly its own.